Hello everyone, and we will continue with building our model. So we would now go on to build our models in our model builder function. So before we build our model, I will just talk about what kind of model we are going to use. So we are going to use a transformer model. So if you've not heard of a transformer model before, I would leave a link in the description, and then you can read all about it. There's also so many videos on transformer models. So it's the state of the art in natural language processing. So you can use it for sequence to sequence predictions, language translations, sentiment analysis. Um, yeah, so many things. So it's composed of an encoder part, which is the first part of the model, and then a decoder part. So the encoder will encode your inputs into some compressed representation, and then the decoder will decode those compressed representations. So if you have something like an English to French, if you want to perform maybe English to French translations, you give your English input, and then it will be decoded into some representation, which will be decoded by your decoder, and then you get your French translation. So I'll leave a link in the description, and then you can read and also know about all the parts of the model, especially what a multi-head attention is, what an input embedding is, which has already been used before this model came about. Why do we do add and normalization and things like that, positional encoding and all that. So I'll leave a link, so check out the link, and also other videos on YouTube. You find so many, so just look at them. In our model, we are only using it for sentiment analysis, predicting 0 or 1. So we are not doing any sequence to sequence predictions. So we don't need this huge model. I'm just going to simplify it. So we are just going to use the encoder part, and then I'll just add some simple dense layers, and then add a sigmoid function, and then we are done. I think it will give good results. So just this layer, just some dense layers, and then our sigmoid function to give us our output probabilities, because we are doing a binary classification problem. So actually, so this is the model that we are going to be using. So we have the encoder part, and then some feed forward networks, and then we get some output probabilities. Okay, so we'll go ahead now and then write our model builder function. So as you can see, I've partitioned my screen um, into two parts so that I can see my um, neural network architecture whilst I'm building the model, so that you can follow what is going on. And then, so let's go on. The first thing we have to do is to I'm going to use Keras, so I'm going to import the layers function. So from Keras, no, so TensorFlow dot Keras import layers, right? And then I'm going to define my model builder, model builder, right? Now, I'm going to have my first inputs, right? My first layer. So we are going to use, so in Keras, there are two ways to write your models. You can use a sequential model, so a sequential style. So if your model is just stack layers upon layers, you can just write them sequentially. Here, it's not a sequential um, type of model, because you have some connections going to other layers which are before some other layers, and yeah, so we don't have kind of a sequential connection. So it's, you have to use a functional type of connection. So if you don't know functional and sequential, um, you can also learn a little bit about what how to write layers in Keras and in TensorFlow. I'll leave a link also in the description. Just go through the basics of writing neural network models in Keras and TensorFlow. So first I'm going to say inputs. So tf.keras.input. So every Keras model has to start with an input, right? So I'll say shape. So what's the shape of my input? So it's just a one-dimensional. Every instance in our data set, every input or every feature is just a string, right? So that's what we are going to use. And then our name is, so what is the name? The name is the name of your column, right? So here the name is the name of um, the usually when you are building your model, you will just say, you just give it any name you want. But here the name is really important. The name is the name of the column that your data, your input is referring to. So we know that it's transform name and then review, right? And then our D type, our data type is what? TF.string. Now we all know that when we are using Keras or neural networks only work with numbers. They don't work with strings, right? Therefore, when we were doing our transformation, we should have transformed our our inputs into what numbers, right? And then used it to do whatever we want to do. But we didn't do that. So now we have to do that. So the first thing we will do is to um, so we have to just transform our inputs um, into numbers, and then we can use an input embedding layer, right? So that the input embedding layer, what it does is to transform our inputs. So if the words are similar or the text is similar, it just transforms our input into another dimensional space. So if I have 1,000 dimensional input, it can transform it into maybe a 64 dimensional input, and the words that are similar would lie in the same plane. So obviously text that is similar to each other would lie on the same plane, will lie closer to each other. So that's what an input embedding is, right? I'll leave a link there. You can look at what um, or you can do further reading and look at what input embedding really does. um, yeah. So, but the good thing is that people have trained a lot of input embedding layers on online on TensorFlow Hub. TensorFlow Hub is a place where you can submit your train models, and people can use those train models in their own model or in those layers. So people have trained a lot of embedding layers, and you can just use one of them in your own um, work without doing so much work. So one of the ones I like using is called Universal Sentence Encoder. So yeah, you can read. I'll leave a link also. So the universal sentence encoder encodes text into high dimensional vectors that can be used for text classification and a whole lot of stuff, right? So so the input is a variable English text, and the output is a 512 dimensional vector, right? So actually this input embedding stuff can also do how do I say it can also do transformations. That means it can also clean text and all that. So actually we don't need to actually clean our text or perform any transformations when we are like pre-processing. So the model does not require pre-processing the data before applying the model. So it performs the best effort text input pre-processing inside the graph. Yeah, but the pre-processing we did was to show you how to um, do pre-processing, natural language pre-processing in TFX. So you see, it's pretty popular. It has 1.4 million downloads. So a lot of people trust. It's just that it has a large size, but a lot of people trust using um, this model. So we are going to copy this. So I'm going to copy this whole thing. I'll leave a link to the of this, and then we are going to use this in our own work, right? So let me just go back to that, and then let's have our. So the first thing um, I'm going to do is I'm just going to put this here. I'm going to put it before our model, our function, and then I'm just going to cut this and then put it at the top, just like that. You can put it anywhere you want, but I like putting it here, right? And then let's continue with our writing our functions, our code. So the next thing we are going to do is we are going to reshape our inputs. So actually our inputs are two-dimensional, right? It has an extra axis that we don't need, even though I put it here as one. It's actually some two-dimensional input. So we are just going to reshape our inputs so that we can use it for our embedding um, layer, right? All right. So I'm going to say reshape narrative, and then we are going to say tf dot reshape inputs -1, right? And then we are going to pass this reshape narrative into our embedding layer. So we say embed, and then we just pass it reshape narrative, right? And then I'm gonna say I realize that anytime I use this layer, I keep getting some funny errors. I have to reshape that layer after I apply it. So yeah, I don't know why, but yeah, we are just gonna do that anyway. So layers dot reshape. So as the documentation said, it has a 512 dimensional output. So we're just gonna um, so input shape. Now as you can see, the input and the output shape is no different. But then if I don't do this, I'll get an error. I don't know why I always get that error anytime I use this model, but yeah. Now 512 dimensional input is very high. So I'm just going to, before we go to this, so we are done with our input, we're done with our input embedding. Before we go to our multi-attention head, I'm going to apply um, a feed-forward neural network here to reduce the dimension of our input embedding, right? So I'm gonna say layers dot dense and then 64. So 64 is our number of neurons that we want in that layer. And then for our activation, I'm going to use elu. And then for my kernel initializer, I'm going to use glorot uniform. So if you don't know what all these kernel initializers and all these things are, I highly recommend you to just take a simple 1 week course on neural networks, and yeah, you get to understand all these. So after specifying this dense layer, I didn't put this dense layer, but I'm just using it to reduce the dimensionality. So I can go ahead and do my multi-attention head. So I would say attention output. So it's layers dot multi attention head, And for my multi-attention head, I need to specify my number of heads. I will just say it's 2. And then my key dimension, I will just name it to be 64. So if you have watched a YouTube video on what a multi-attention head does, then you can understand what its number of heads and what its key dimension. And then we can see that we have 3 inputs. So from our input embedding, so we have to specify 3 of them, XXX, right? And then our attention output again. Now I'm going to add a dropout after some of the layers. So after an attention output or a dense layer, I will just add dropout. Dropout is used for regularization so that our data does not overfit, right? That we can have good generalization. So I'm going to specify a dropout rate of 20%, so 0.2, and then that is so I'll pass the input, so that is attention output. And then the first thing, one thing I'm also going to do is, so the next after attention we have what? Normalization, right? So I'll say, let me just call it out1, right? So I'll say layers dot normalization, layers dot layer normalization, right? And then I have some epsilon here, that is to prevent division by 0. And then the normalization is add a normalization. So from our input embedding and what our attention, right? So the output of our input embedding, which is the layers dot dense, and then we add it to our attention output, right? So basically that is it. And then after add a normalization, we have a feed forward network. So I'm just going to name it fn output. So I'm going to say layers dot dense, right? And the ff dimension. So what is the number of dimensions that you need? I'm gonna say 64. I'm just gonna use 64 neurons here too. And then we have activation. Just gonna name it elu, right? And then we have kernel initializer. I'm just gonna say glort uniform, just like we did here, right? And then the output is out, right? And then after that, I will add another dropout layer. So I will say fn output layers dot dense ff. So ff dimension 64. I should have just used the constant for that. And then kernel initializer. No. Yeah, let me just add another yeah, since I've already written it. I wanted to write dropout, but I ended up adding another hidden layer network. But let me just go for it. Yeah, and this hidden layer, I'll just use a normal linear activation function. I will not apply anything. So ffn output. So now let me add my dropout. So layers dot dropout, and then we have our dropout rate, and then ffn output, right? So after that, after our feed forward, we have what? Add and normalization. So we have x, which is equal to layers dot layer normalization, and then we have epsilon 1 e minus 7. So our add and norm is output of the feed, output of our first add and norm, and then output of our feed forward. So it's out1 plus f output. That's like that. And then we have our average pooling. So we say layers dot global average pooling one dimensional. So it's one dimensional average pooling. We are not going to specify any parameters here. And then I'll have dropout again. So I'll say x layers dot dropout rate, and then I'll say x, and then after that I'll add another dense layer. So x is layers dot dense. I'm gonna specify 32 here, and I'm just gonna copy this so that I don't waste time typing. I'm just gonna copy this because it's the same thing we're gonna use, and then our input is x, and then x is equal to layers dot dropout again rate, and then x, and then finally we have our outputs. So we say layers dot dense is just one output, that's either a 0 or a 1, so we just need one output, and our activation, if you have guessed right, it will be a sigmoid. And then so this is our model, neural network model. So then we need to tie everything up. So first, so we need to specify, now your model doesn't know what your input is and what your output is, so you have to specify that your model is a tf.keras.model, and your inputs is equal to inputs, so your input is equal to this inputs, and then your outputs is equal to that outputs. So then everything ties up, right? And then we have to define our model training parameters. So model.compile, right? So then we have our loss function here. So loss will be equal to what? If you guessed it right, we are going to use binary cross entropy. So if you don't know what binary cross entropy is, go to YouTube and find out what that is. So optimizer. So if you don't know what an optimizer is, so what is your optimization function that you're going to use? Gradient descent, Adam, Nadam, yeah, things like RMS prop. So all this. So keras dot optimizers dot Adam. We are going to use Adam, and then we're going to specify a linear rate of 0.01, which I know you don't have to specify, but I'll specify it anyway. And then our metrics, what are we tracking? So we have tf.keras dot metrics dot binary accuracy, right? I want to track our binary accuracy, right? And then when we are done, we would like to print the model. Now this is so that, yeah, if we run our model and it works, then it means that our so print model dot, and then the next thing is we have to return our model, right? So this is all for our model builder function. So take a while, take some time, and then go through the code and try and understand all the parts of the code. All right. So we will leave. We will finish here. We have two more functions to run, which are very, very, very important. After that, we would continue with our with running our model. So see you in the next video.